Okay, so at this point now we need to know how to evaluate integrals of the weighting functions as well as their derivatives and products and so on. And the rules for doing this have been worked out. These weighting functions are sometimes referred to as triangular coordinates. And the reason is because one way to think about this function w sub I is as the ratio of the area of two triangles. So let's draw this element E. This is I. This is J. And this is K. So if we think about what contours of constant w sub I look like, we know that w sub I is going to be 1 here, and it's going to be 0 here and here. And actually contours sort of look like this, right? They're linear like this. And so one way to think about what w sub I actually is if I'm at this point right here, let's call this point P with coordinates x, y. So Wi then is the ratio of the area of this triangle that connects point P to J and K, so this area, to the triangle that is the entire element. So W sub I is equal to the area of A JKP over A and JKI. And you can sort of see why this would be true, right? If I look at any point along this line right here, because the area of this triangle is 1/2 the base times the height is the same, and the base is the same, and so W sub I is constant along this line, or this line, or this line, and that's exactly what we want. That's exactly what we want. So, if I think about contours of constant w sub I, it would be like this. This is J, K, I. This is w sub I equals 0. This would be 0.25, 0.5, and so on. And w sub J would be the same thing, but the lines would be parallel to that base. So you can go through, I guess it's section 9.1.3 in the book, and it will basically show you how to derive the function w sub I, which is a function of x and y, w sub j, which is a function of x and y, and w sub k, which is a function of x and y. But it literally is just taking the area of those two triangles. It's taking the area of the triangle defined by the coordinates x sub y, x j, y j, and x k, y k, and dividing it by the area of the triangle defined by x I, y I, x j, y j, and x k, yk, right? So this triangle divided by this triangle. So it depends on x and y. It also, of course, depends on the coordinates of the nodes that make up the element in question. So we can write down one of these. W sub I is a function of x and y is equal to 1 over bijk. We'll come back to what this means. Multiplied by xj yk minus xk yj minus x times yjk plus xjk times y. So these are obvious, I guess, right? This is the x coordinate of node j and the x coordinate of node k, the y coordinate of node j, the y coordinate of node k. yjk and xjk, and then also bijk are a little less obvious, right? So yjk is equal to y sub k minus y sub j, right? So it's the y distance between these 2 points. If I come over here, it's this y value, this y value here, minus this y value here. This is y j k, and the same thing, x j k is x sub k minus x sub j, right? So it's x sub k minus x sub j. It's this distance here. This is x j k, and then finally b I j k is equal to x I j y j k minus x j k y I j. It's also equal to the 2 times the area of the element. So the area of the element is equal to the absolute value of b I j k divided by 2. And actually, if I, j, and k are defined, if these nodes are defined in a counterclockwise fashion as they are here, right? I, j, k, it's counterclockwise, then bijk will always be positive, and so you can take away the absolute value. So the rules for using triangular coordinates then, let's see, if we write wi again up here, wi is equal to 1 over bijk times xj yk minus xk yj minus x times yik, that's right, yjk plus xjk times y. So I'm going to need to have derivatives of this as well as integrations of this over elements. So the derivatives are pretty easy. The derivatives are, let's see, dwi dx is equal to, well, here's x, so it would be minus yjk over bijk, and dwi dy is xjk over bijk. If I would do the same thing for wj and wk, I would get dwj dx is equal to yik over bijk, and dwj dy is equal to minus xik divided by bijk, and dwk dx is equal to minus yij over bijk, and dwk dy is xij over bijk. So the other thing I'll have to do is integrate either w sub I or w sub I times w sub j or things like that over the area of an element. So the rule for that is wi to the a, wj to the b, wk to the c, dA is equal to a factorial, b factorial, c factorial divided by a plus b plus c plus 2 factorial times 2 times the area of the element, which is also bijk. So with these rules then, we can begin to think about how to assemble at least c and k and g. Right? Q we'll have to come back to, but we'll start with c. So c is equal to the integral over the entire computational domain of rho c times w transpose dA. And we're going to assemble this element by element, right? So the way this looks, if I were to write it out, is this is so let's do this, rho c times, so this would be the integral of I guess it would be w1 times w1 dA, and then I have right next to it w1 times w2 dA. And if I go all the way over here to the end, I'll have W1 times Wn dA. And if I go down the bottom row, I would have Wn W1 dA all the way over to Wn dA. And if I just look in any arbitrary row I, so this might be row I, and column J, so this is column J, this is going to be the integral over the area of Wi Wj dA. So this is what it looks like in general. If I look at this inside of any element, what you're going to find is only, how many of these? Only 3 of the W's are not 0. So so inside of any element, so we're gonna write this inside of one element. So we'll be assembling the elemental capacitance matrix, which is just the integral over the area of an element of rho CW times W transpose dA. And you can see then that inside of this element, if this element is defined by nodes I, J, and K, only Wi, Wj, and Wk are not going to be equal to 0. So what that means then is there's only going to be 9 non-zero elements, right? In row I, J, and K, and in columns I, J, and K, there will be entries that will not be 0. So I can write the elemental capacitance matrix by keeping that in mind. So the rule then for assembling the element capacitance matrix looks like this. It's density times specific heat capacity, and we'll put a little E here to indicate that this is the value of these properties inside that element. So we might allow specific heat capacity or density to vary over the computational domain, but within each element we're going to use a constant set of properties. And this is a big n by n matrix, but within element E, defined by I, J, and K, there's going to be only 1, 2, 3, 4, 5, 6, 7, 8, 9 non-zero elements, and they're all going to look like this. So this is going to be Wi squared, this is row I and column I, dA. This is going to be Wj squared dA, this is in row J and column J, and then this is Wk squared dA, this is in row K and column K. And these off diagonals, this will be Wj Wi, this will be Wi Wj, Wi Wk, Wj Wk, Wk Wi, and finally Wk Wj. So one thing you'll notice is that the capacitance matrix is, first of all, a lot bigger and more complicated than it was for finite differences, but it is not diagonal anymore, but it's definitely symmetric, right? These two guys have to be the same. These two guys have to be the same. Alright, so the last thing we can do here then is figure out how do I evaluate these integrals? What are these actual quantities in terms of properties of the mesh that I'm dealing with? So we said that in general, the integral of Wi to the A, Wj to the B, Wk to the C dA, evaluated over the area of the element, is equal to A factorial, B factorial, C factorial, divided by A plus B plus C plus 2 factorial times 2 times A sub B. So for us, let's see, if I'm on the on diagonal, so for example Wi squared, this is going to be A equals 2, B equals 0, C equals 0. Alright, so this is going to then be 2 factorial times 0 factorial times 0 factorial over 2 plus 0 plus 0 plus 2 factorial times 2a sub e. So 2 times 1 divided by 4 is 4 times 3 times 2 times 1, and then multiplied by 2 a sub e. So that cancels. I'm left with this is equal to, let's see, this is 12 divided by 2 is 6, so a sub e divided by 6. So this guy here is a sub e over 6. This guy here is also a sub e over 6. And finally a sub e over 6. These off-diagonal terms, so these 6 additional terms, we have to do separately. So let's do, for example, wi wj dA. So in this case, a is equal to 1, b is equal to 1, and c is equal to 0. So this is going to be 1 factorial, 1 factorial, 0 factorial over 1 plus 1 plus 0 plus 2 factorial times 2a sub e. So this is 2a sub e divided by 4 times 3 times 2 times 1. So those cancel, and I got a sub e over 12. So all of these off-diagonal terms are a sub e over 12. So C then, within each element, is going to be a big n by n matrix, and we'll have these 9 non-zero terms, I, j, k, I, j, k. Let's see, I can factor out of these rho times c in the element times the area of the element divided by 12, and that means that this is going to be a 2 and a 2 and a 2, and then everything else will be a 1. Like that. So that is how I assemble the capacitance matrix inside of every element. And then if I want the global capacitance matrix, I just add all of these together. Recall that Bij, which is a quantity you can get from the coordinates, is simply equal to 2 times the area of the element. So if I want the area of the element, I just compute Bij and divide by 2. Another thing to sort of note here is that if I add up all these elements, so this is 4 plus 4 plus 4, this is 12 divided by 12. If I add up all these elements, I get the heat capacity of the matrix. So what I'm adding to the capacitance matrix is, when I deal with any element, is going to be the heat capacity of that element. I'm just smearing it out, though. I'm smearing it out over all these different entries in a way that I didn't do in finite differences. In finite differences, I just put it at one spot, right? So you can sort of think of this as taking 1/3 of the capacitance and assigning it to node I, 1/3 of the capacitance assigning it to node J, and then 1/3 and assigning it to node K. So we have to do a similar sort of thing for K. Right, so again, we have to remember the formula for K is the integral over the area of K times dw dx times dw transpose dx plus dw dy times dw transpose dy times dA. And again, we're going to deal with this by doing this area integral one element at a time. So K, the elemental conduction matrix, is the integral over the area of the element. Then we can bring the K out. So again, we may have K, thermal conductivity, that varies over the entire cross-sectional domain, right? So it could change, but within any element, we're going to require that it be constant. So this is the K inside of that element. And we'll have dw dx times dw transpose dx plus dw dy times dw transpose dy dA. Right, so I can evaluate each of these and then just add them up to get K. K is the summation from E equal 1 to ME of K elements, just like C is the summation from E equal 1 to ME of the elemental capacitance matrix. Alright, so within any element, I know that the W transpose looks like this. It's a bunch of zeros, and then I get the WI, and zeros in WJ, and zeros in WK. So I need the partial derivative of this with respect to x and with respect to y. So dW transpose dx is equal to a bunch of zeros in dWi dx, dWj dx, dWk dx. And if I go back and look at my rules for these guys here, I find that this is, so dW transpose dx is equal to a bunch of zeros, and I have minus yjk, a bunch of zeros, and then yik, and a bunch of zeros, and minus yij, all over 1 over bijk. So minus yjk over bijk is dwi dx, and so on and so forth. Right? So if I now take, let's see, dw dx and multiply by dw transpose dx, I have here a row vector, so this is, a column vector, 1 over bijk, and it's a minus, so it's a bunch of zeros, it's a minus yjk, yik, and minus yij, and then I'm going to multiply that by 1 over bijk, and a bunch of zeros, and minus yjk, yik, and minus yij. So these I can pull out, and I get then that this is equal to 1 over bijk squared, and this becomes a big N by N matrix, right? So if this is I and j and k, and this is I and j and k, then in row I, I'll have 3 non-zero elements in columns I, j, and k, and the same thing for row j and row k. So this will be minus yjk times minus yjk, so yjk squared. This is going to be minus yjk yik, and this will be yjk yij. Now we can continue. This is minus yik yjk, this is yik squared, and then this is minus yik yij, and finally this guy is yij yjk, minus yij yik, and finally yij squared. So it turns out then that this guy right here is at least half of what we're trying to do right here. Right? It's this big matrix here. And actually the other interesting thing is, these gradients are not a function of x or y inside the element. Right? You notice there's no x or y inside of here. So they can be removed from this area integral, and I'm left with just integrating the area, which is of course just the area. So with that then, my rule for KE is the conductivity in the element, and then I have this dW dx times dW transpose dx plus dW dy dW transpose dy, where these are not a function of x and y, and therefore I've pulled them out of this integral over the area of the element, and this just becomes the area of the element. Right. As we work through this, then we get the following formulas for how we put together the element conduction matrix, and it looks like this. We have the conductivity of the element times the area of the element divided by Bij squared. And then we have a big n by n matrix, and it's got 9 non-zero elements. And where this is I, J, K, I, K. And this is then KII, and so on, KJI, and finally KJK. Sorry, this is actually KKI, KJ. And each of these has a formula, which is KII is equal to YJK squared plus XJK squared. This guy, KIJ, is equal to minus YJK, YIK, minus XJK, XIK. And finally this guy is KIK is equal to YJK, YIJ, plus XJK, XIJ. And the conduction matrix is symmetric, right? So this guy is equal to this guy. So KJI is equal to KIJ. KJJ is equal to YIK squared plus XIK squared. And KJK is equal to minus YIK YIJ minus XIK XIJ. And again, symmetric, so KKI is equal to KIK, KKJ is equal to KJK, and the last one here is this guy, which is YIJ squared plus XIJ squared. So this, of course, multiplied by that is how I put together the element conduction matrix. And if I want K, it's just a matter of adding all these together like that. So K is still symmetric. It's just added together. It's just assembled a little differently than it was for finite differences. Okay, so let's do the last one, which is our G, our generation vector. And if you remember, for finite elements, what we found that this was also related to an area integral over the whole computational domain of W times G triple prime dA. And so we're going to put this together one element at a time as well. So G inside of any element is going to be G triple prime within the element. So just like K in rho and C, this may vary across the domain, but within any element it's going to be constant. So it'll be a constant inside of this area. And then we'll integrate over the area of the element times W dA. So this is then G for the element is equal to G triple prime for the element times, this is a big vector that has inside of this element only entries in rho I, rho J, and rho K. So this will be the integral over the area of the element of Wi dA. This is going to be the integral over the area of the element of Wj dA. Finally, Wk dA. So if we look at this, we know how to integrate these things over an element's area. This is Wi dA. So this is a case where A is equal to 1, B is equal to 0, C is equal to 0. So this becomes 1 factorial times 0 factorial times 0 factorial divided by 1 plus 0 plus 0 plus 2 factorial times 2 times the area of the element. So this is going to be 2 times the area of the element over 3 times 2 times 1. So This is the area of the element divided by 3. So our elemental G vector is equal to G triple prime in the element times the area of the element divided by 3. And then I have a bunch of zeros and a 1 in row I, and then a 1 in row J, and a 1 in row K. And again, you can see that what we're doing is we're taking the total generation that occurs in that element and we're breaking it into 3 parts. And we're assigning a third of it to node I, a third of it to node J, and a third of it to node K. Right? We're basically saying if this is our element, I can do something like this and say, okay, everything in that region is going to be assigned to I, everything in this region is going to be assigned to K, and everything in this region is going to be assigned to J. And again, if I want G, then it's just the summation from E equals 1 to the number of elements of G elemental. So again, the construction of, we know how to construct C and K and G now, and we do this, we construct these element by element rather than node by node. So in finite differences we did this node by node. Here we're going to do it element by element. Alright.